started. In this video, I'm going to discuss about Wagner-Milwid rearrangement. It's basically the carbocation rearrangement, and the carbocation always has tendency to rearrange to a more stable carbocation, and this always happens in a reaction like E1 elimination or SN1 reaction. Let's discuss about the E1 elimination. So this one substrate undergo dehydration to give rise to this product. Let's look at the mechanism. The first step is apparently the protonation. So the water molecule leaves behind a carbocation. This is a secondary carbocation, so it will have to rearrange to a more stable carbocation. Let's look at this one. Can this hydrogen migrate? No, because that will give rise to a double bond at the bridge head, which is against the Bred's rule. So which group can migrate? So the best group is this methyl group, because the migration of this will give rise to a carbocation that is tertiary and is also more stable compared to the hydrogen migration or hydride migration. So this intermediate, which is the finally a tertiary carbocation, which does not have to rearrange further, so it will simply lose a proton to give the final product. It is another example of my carbocation rearrangement. These are actually a synthetically useful reaction, so you get camping from isobornyl and the carbocation rearrangement happens there. So the first step again, the protonation, so gives rise to a carbocation. Again, this group cannot migrate, but this group can. This methyl group cannot migrate. However, this group can migrate to give rise to a tertiary carbocation. This is no more a bridgehead. This is no more a bridgehead, so you don't have to worry about. And that again flip to give you this species, which can simply lose a proton to give rise to the product. You see here, that is the reason for the reaction to go this direction. There is no other possibility for the reaction to go any other direction, because the migration of this hydrogen will give only the secondary carbocation. However, the migration of this group will give rise to a tertiary carbocation, which is more stable. Now let's look at an example which involves electrophilic addition. So in this case, again, the first HCl is added across a double bond. However, the rearrangement also occurs. So the first step, apparently the protonation, which gives rise to a tertiary carbocation. You may ask a question. This is already a tertiary carbocation, so it does not have to rearrange. But there is the rearrangement also happens if the compound can relieve the ring strain. So in this case, this is a 4-membered ring. So upon rearrangement, it gives rise to a carbocation that is secondary, but the ring strain is released. So now the chlorine can simply add to give rise to this product. So we have seen the carbocation rearrangement in E1, SN1, and an electrophilic addition. All these are synthetically useful reactions. This is not just an hypothetical compound or hypothetical reaction. These are synthetically useful reaction for imported compounds. Thank you.